and welcome to part 3 of the atmosphere topic. So far we have looked at the global heat budget, we have looked at the variations in insolation and why we have them, and now in this part and part 4 we're going to look at how those variations, that surplus of energy and that deficit of energy, are redistributed around the planet so that those in the northern poles and southern poles don't actually freeze to death, and we do get people living in places like the UK, which would otherwise be a lot colder. So let's go over to the model and have a look at how this is redistributed. We have our sun away over here somewhere, again, not small, just very far away. And the light comes down and hits the equator. So what we're going to do first of all today is we're going to pop our equator in, just so we know roughly where we're looking at. Let's pop our equator in, and then it gives us a working point. So we've got our equator there. Probably what else we want to add into our diagram around is just our atmosphere to give us some context about where this is. And I'm not saying our whole atmosphere. This is really just going to be the troposphere, which is where most of our weather patterns happen. So at the equator, we've said before, we have a surplus of energy, an excess of energy that is making the air warmer, making the water and the land warmer. And what happens when that occurs is that air starts to rise. So at the equator, we have rising air, and this is known as low pressure. So this is a low pressure zone where air is starting to rise. But when it reaches the ceiling of this troposphere, what happens then is it actually doesn't go any higher, so it's pushed out to the side and it's pushed away north. And once it gets far enough north, it actually then starts to cool, and as it cools, it begins to sink back down. Again, can't sink any lower than the planet, so it's actually then forced back south, where it slowly warms up again and joins in to the warm area, which then moves it back north. So this is going to be number 1. This has then created an air cell where we've got this low pressure that comes up, moves north, and then sinks and returns to the equator, creating what's called the Hadley cell. And now this is driven by the temperature, by this excess of heat at the equator that creates air pushing up and then moves north. The opposite occurs at the poles. Because the poles are colder, they make the air sink and they make it drop down. So if we take our air at the poles and push it straight down, this is called high pressure. If you think about it, the air is heavy, it's sinking, and as that heavy high is going downwards. Now it's the complete opposite to our Hadley cell, where the main driver in our Hadley cell is the fact that the air is being warmed at the equator. This time the air is being cooled at the poles and sinking it down. But again, it can only sink so far as the surface of the Earth. Then it is deflected south. It would actually happen this side as well, where it's deflected south here, but we're looking primarily at just the one section, the cross section just now. So it's then deflected south until the same thing occurs, that it gets warmer. Now it happens around about 60 degrees north. It gets warmer enough that it then rises back into the air, hitting that troposphere, and is then deflected north again, where it cools and sinks back to the Earth. Now this is our second cell. But because we've got one to go in the middle, I actually call this number 3, and this is the polar cell, named after the fact it's at the poles, found at both north and south poles. It used to be that we only actually ever thought that these two, and these were going back and forwards, but we actually have a third one. And the third one is not driven by the temperature, it's actually driven by friction. As the Hadley cell is dropping down, it also pulls other air from it down with it as well and forces that away north. And as the polar cell is rising north, it is actually pulling in air and forcing it upwards as well. And it diverges and converges at these two other cells. So the Hadley cell goes to about 30 degrees north, and the polar cell drops down to about 60 degrees north. So between that 30 and 60 degrees, we actually have this third cell known as the Ferrel cell. And this is our three-cell model. So we now have the Hadley cell, the Ferrel cell, and the polar cell that all work together to actually distribute air. How does this actually even out our surplus and our deficit that we see in our solar insolation? Well, this air that's moving across the ground is not actually like imaginary, it's actually there. That is what wind is. And these are our surface winds, and our surface winds are actually moving air from one area to the next. So if we bring in a little help, we might ask like Princess Poppy from Trolls. So if she starts at the equator down here, she could be like an air molecule that is carried up into the air and then transfers along and then sinks back down at 30 degrees north. But instead of returning to the equator, she is then carried by the Ferrel cell further north. And then at 60 degrees north, she gets carried up into the air again and then travels north to the poles, where we've got this warm energy from the equator that has now made it all the way to the poles. And this is where we also then see the reverse, that if Poppy is in at the poles, she's cooled down, she's really cold, and then travels south, is picked up by the Ferrel cell again, travels south, cools down, but this time travels back to the equator. And now we can see how cold air from the poles is transferred back down to the equator. So an easy way to remember this is it goes high, low, it's off to the poles we go.
Hi ho, it's home from earth we go.
And the one last thing to add into this is not just happening in like a single cross section. This is happening across the whole of our planet. This is like a fully 3D object that is happening everywhere. And it doesn't just happen in a linear way. These surface airs are not just going up and down. They're, because our Earth spins and it moves around, it actually deflects our winds around. So between this 30 degrees north and the equator, our winds are actually deflected that way. So the winds in the northern hemisphere are deflected to the right. Between the 30 and 60, the winds are deflected that way. And then as they're coming south, they're deflected that way. And these winds have their own names. So the ones at the top are our polar winds, or our polar easterlies. So this is our polar easterlies. The ones between 30 degrees and 60 degrees are called our westerlies. And the ones between the equator and the 30 degrees north are called the northeast trade winds. So the northeast trade winds, and this will become more significant as we look on to the ITCZ in a later part of this topic. So that is the three-cell model. I hope it helps. We remember as well that this exactly happens in the southern hemisphere. Everything has flipped. So the Hadley cell is still the one closest to the equator, then the Ferrel cell and the polar cell goes down to the Antarctic, and the trade winds all happen that way as well. They're deflected to the left instead of the right, but it happens exactly the same on the southern hemisphere. So all the way that this warm energy from the equator has been spread out to the poles, and the cold heat at the poles has been spread back to the equator. So we get a balancing fact, and that is how that's one way of how our atmosphere is balancing itself out.
And this is notes. Go to this section, pause video here to write them out.
Come back for the next part, how we'll see how oceans play their part in balancing out this heat and insulation imbalance as well.